All right, I think it's time to start. So first, we have released the date, which requests you to tell us your project selection. I think it's next Friday. So please submit the simple PDF, half page, whatever, and just telling us, which project you want to do, paper reading or research project. And if you're doing paper reading, please give some attempted 3 papers. It's not required to fix the list right now. You can just grab 3 papers which you think you might want to read through, put them there, and then later if you feel like I'm more interested in other papers, and then just update me or the TMs. Okay. And also we have extended homework 0 for 1 more week. I think that should be enough to finish all the problems. And also, again, we got office hours every weekday. Please do not hesitate. If you feel it's really difficult, you want to consult with some guy, like come to the office hour. Okay, so let us continue with the basic definitions regarding probability, right? So in the last lecture, we talked about how do we compute the expectation for a function of a random variable, right? So general, if you want to do the expectation for any random variable, you just do the integral if your probability density is continuous. Right? If your probability density is discrete, you're dealing with a discrete valued random variables, you do the summation over the probability mass, right? So if you put some transformation on your random variable, and then you want to calculate the expectation. So you just replace in the integral the random variable by the transformation on random variable. That's it, nothing else, right? And similarly, in the discrete case, you just add up the math, all the possible values that the random variable can take, and then multiply it by the probability mass for that value, and then sum over. And then another very important property for random variable is called variance, right? So variance just means on expectation, how long your random variable can get away from its mean, right? So we all know that the random variable has some property. It shouldn't be too far away from the mean, right? Or in other words, the more distant your random variable take the value from the mean, the less of that chance, right? So variance actually gives such kind of a measurement. So the variance is defined as this, right? This is just another expectation. So the expectation of the square difference between your random variable and the mean. That's it. And this is equivalent to calculate the expectation of the square of random variable subtracted by the square of the expectation. Right? So this is some kind of a basic knowledge point, or everybody should have saying this before, right? So the expectation of the square difference between the random variable and its mean is the same as the expectation of square subtracted by square of the expectation. Okay? So the variance is a measurement of the spread of the distribution, right? So if you draw a random variable, it's a density distribution in this way, we can expect that the variance must be larger than a more spiky distribution, right? And another common used statistic for random variable is called standard deviation. Right? Standard deviation just tells you what's the exact distance, right? So the variance is a square of distance, right? So you want to make the same unit, so you take the square root over the variance x. So you can imagine that this is your mean, right? So the standard deviation actually measures how absolute distance between your value and its mean. Right? and the variance is just the square. And a very common used distribution is called normal distribution. So normal distribution is determined rightly by the mean and the variance, or standard deviation. Okay. So we say X is normally distributed with mean mu and standard deviation sigma. That means its density has this exponential form, right? So I'm not gonna read through this form. I believe everyone has heard of it and quite familiar with that. And actually, I mean, although quite simple, the normal distribution takes kind of like a central role in Bayesian statistics, frequentist statistics, and also machine learning. So you see later that many powerful machine learning models like Gaussian processes, they're underpinned. I mean, they're grounded on this normal distribution, and their calculation techniques are all based on, manipulating Gaussian distribution, multivariate Gaussian distribution, conditional Gaussian distribution, all kinds of stuff. So we need to be very, very familiar with this family of distributions. So recall that given two events, A and B, we can talk about the probability for the intersection of the events A and B, right? So basically, this tells us the probability that both A and B happens. Right? So we actually emphasize that A intersection with B is different with A union with B. Right? So the former expresses an event that A and B both happens. But the second one has another meaning. It means that A happens or B happens. So it includes several cases, right? If you can use a figure to represent them, like, and this is A, this is B, right? A intersection with B is actually telling this set, right? The overlapping part. But if you're talking about A union with B, it's actually a much bigger event. So they're different. And when we talk about the joint distribution, we're referring to the probability of this, the intersection with B. So don't be confused that here. Don't we like if you write a joint probability that is big X, I mean random variable X smaller than this guy, and random variable Y smaller than this guy, this simply means the intersection of these two events. It's not the union of these two events. Okay. So given two random variables X and Y, we can talk about the intersection of the events of those variables defined, and the distribution defined in this way is called the joint distribution, and it's defined this way. So this is called the joint cumulative distribution, right? And then we can take derivatives over the joint cumulative distribution, right? So actually you take a second order derivative over X and over Y, you get the joint probability density function for X and Y. So by the way, if I'm just assuming everyone has heard of it, this is just to give you some refreshment, right? If you feel kind of uncomfortable or feel weird about any point, just interrupt me. Right? Otherwise, I'm gonna go through this quite smoothly. And in another way, given the joint probability density function, we can recover the cumulative density function by integrating the PDF, right? So, but because you got like multiple random variables, your integral is kind of multiple integrals, right? You're gonna integral with each random variable. So once you have a joint probability density, right? And then we can calculate the marginal density for each individual random variable, right? X and Y. And doing this is pretty straightforward. You just integrate out one variable, no, the other variable over the joint density. Right? So P of x, the marginal density of x is just the integral of the joint density over y. Right? And P of y is integral of the joint density over x. Right? And for the discrete case, well, we just do the summation. So in a broader sense, you can view integral and summation kind of exchangeably, because just one is defined as limit of the summation, right, in the infinitesimal areas. Right, the second one is just to do the summation. So here just giving some code examples. I believe this is a pretty straightforward for everyone, right? So if we have two Bernoulli random variables, one is about the weather, it's code or no code. The other is about one guy's status, like he has a running nose or no running nose. So both are binary random variables. So here we give the joint probability mass function, right? So this is essentially a table, right? So from this table, we can easily compute the marginals, right? So if you want to compute the marginal probability of R, whether this guy has runny nose or not, right? What you need to do is just sum over, right? Sum over the rows, right? Okay. So P of P R is 0 is just sum over all the columns. It's 0.5 plus 0.05, 0.55, and PR is 1 is this plus this, right? 0.45. If you want to compute the marginal probability of the weather, right? Say code or no code, right? So you just sum over the rows, right? So P C is 1, C is 0 is 0.5 plus 0.2, 0.7, and P C is 0 is 1 is 0.2, 0.05 plus 0.25, which is 0.3. And also, given the joint density, we can define the conditional density. Right? So the conditional density is defined as the joint density divided by the marginal density. Right? So P of x conditioned on y is calculated by dividing the joint density by the marginal density, which we're going to be conditioned on, right? P of y. And again, we can follow this table to compute the conditional density. Well, I'm not going to go through this because this is relatively straightforward. Okay, a very, very important concept is called independence. Right? So independent random variables. When we talk about events, right? For example, even A and even B. Right? This is in the original probability space, right? We say A and B are independent if and only if the joint probability of A and B equals to the product of their marginal probabilities, right? But when we talk about random variables, remember random variables are kind of mapping, right? It maps the samples in the sample space to some other set. Well, the most commonly used set is the real set, right? So when we say, okay, the random variables are independent, we're actually saying, okay, the random variables outputs or values are independent. And we can show that if their joint density is equal to the product of their marginal densities, then the two joint probabilities, the two random variables are independent to each other, right? So it actually has the identical form when we talk about the events, right? But actually their underlying meanings are different. So just pay attention to this slight difference. So if you want to show this is kind of a theory. You need to prove that. This is a kind of definition. This is a theory. It's not very straightforward to prove this. And if you do the integral on both sides, you can also show that, okay, for the cumulative density function for independent random variables, the cumulative density is also, cumulative distribution is also the product of their marginal cumulative distribution. Conditional expectation, right? As the name suggested, right? Conditional expectation of some random variable x taking another random variable y is defined as the integral of the random variable and multiplying with the conditional density. Right? So here I want to point out a concept which are often, which many people are confused. So if I write down this, is this a constant or random variable? Y is a random variable. Yes, exactly. So just be super careful about that. So if you calculate this, right? So this guy, this integral has integrated out x, right? So this result doesn't contain any x, but this depends. This is dependent on how you take the value of y, right? And y is random. So if you see some formula like expectation of x, condition y, by default you can view it as a function of the random variable y. So it must be random. That's why, I mean, the homework, there is some weird conclusion that requests you to prove, like expectation of expectation, this guy equals to expectation of x. Right? Why you can take expectation outside because this guy is a random variable. And similarly, you can apply the definition in the discrete case. You just add up the mass of the conditional density. Any questions so far? Mm-hmm.
Expectation of x and y.
Mm-hmm.
So how can you define that?
Okay, so this expectation is actually defined as the integral of x and the conditional probability density. This one? Yeah, because this integral is dependent on y, right? Any value of y gives you a different result, right? So it actually maps y to the corresponding conditional density. So you can view it as a function of y. Any other questions? Okay. And if you want to compute the product of two random variables x, y, I mean, again, you can view this is a function of the random variable. And you just multiply x, y with the joint density and do the integral. Yeah. So now let us talk about another important concept called covariance. Right? Covariance, just talking about, okay, how the two random variables are related in the probability sense or statistical sense. So it's defined as follows. Given two random variables x, y, then the covariance of x and y is expectation of the product between x subtracted by its mean and y subtracted by its mean. So again, it is straightforward to simplify it as the expectation of x and y subtracted by the product of their expectations. This actually measures how much the two variables change together. Okay. So if x and y are the same, then this is the variance, right? It's actually the variance. But if x and y are different, then this is just covariance. So, well, roughly speaking, you can say if covariance is bigger than 0, it basically says, okay, if x increase, then y has large chance to increase as well, right? On average. And if x increases yet y decreases on average, then the covariance is negative. And this is another notation, right? We use sigma xy to denote the covariance of x and y. So you can say this, right? X minus mu x times y mu y, right? So if they both change very large, you can imagine the whole expectation is large, right? If one guy changes large and the other changes little, then the expectation of the product is small. So it's kind of like showing how two variables simultaneously change. If they simultaneously change largely, and then that means, okay, they are highly correlated, right? If you like for example, what kind of example is a product? For example, if let us consider weather, the temperature, and how many people are wearing thick clothes, right? So you can imagine if the weather decreases a lot, right, and the number of the people who wear thick clothes will increase as well, and a lot, right? So you can imagine there is big covariance between the two random variables. On the other hand, if the weather increases a lot, and then the number of people who wears the thick clothes will decrease a lot, right? So there's strong covariance, but they are kind of changing in the opposite direction. So you can imagine this is a negative covariance, but with a large absolute values. But in many cases, like they're just slightly correlated, then the covariance is relatively small. Basically, you can say, okay, their correlation is quite weak, but you can't say X, Y are independent.
But if they are
Then their covariance must be 0. So basically, you can view like covariance is kind of second order correlations, but the independence are kind of have a stronger requirement. And then based on the covariance, we can define the correlation of two random variables. This is kind of normalized covariance. You divide the covariance by the standard deviation of each random variables. So you can normalize them between -1 and 1, right? So that you can compare, okay, a bunch of random variables, x1, x2, x3, and blah, blah, blah. You can calculate the correlations, pairwise correlations, and know which random variables are more correlated with each other. Okay, so here is the conclusion. Independent random variables are uncorrelated. So, well, I'm not going to go through this, but I believe this is easy for everyone. But you can basically use the definition of independence to show that the correlation the covariance of the two random variables is simply 0 because the expectation of xy is exactly the product of their expectations. So their difference is simply 0. That means the covariance is 0. But that does not mean the covariance is 0. Then they're independent. These are two different things. Okay, here are a few like conclusions regarding correlations and independence. So independence implies that uncorrelated, meaning that the covariance of two random variables is 0, or their correlation is 0. Okay? But on the opposite way, we cannot see that. Right? If two random variables are uncorrelated, that does not mean they're independent. Right? Or in other words, if we are saying, okay, two random variables are correlated, and then we can safely say, okay, these two random variables are dependent on each other. Right? But on the other hand, we cannot see that. If two random variables are dependent, that is not necessary that they are correlated. They are the same thing. Correlation is a normalized version of covariance, but it's not. It's different from independence.
Correlation is that one variable increases, the other
you can see like random correlation. I mean, yeah, kind of an intuitive way. You can understood that. Okay, you can understand that in this way. Like, okay, if one variable increases, then if one random variable changes, then the other random variables is gonna change on average. But that does not necessarily mean this. I mean, if one random variable changes, but yet another random variable on average does not change, this does not mean these two random variables are not are independent. Any other question? Okay, so those are like very fundamental concepts. I believe everyone has heard of them before.
And what circumstances the uncorrelated divides the independent? And can be some restriction on the random variable.
Yeah, there are a lot of such kind of cases which can show this. I mean, there are kind of different concepts. It's not.
For example, if they are Gaussian, then you can two random Gaussian.
No, for Gaussian random variables, yeah, they are equivalent. But for non-Gaussian random variables, it's not equivalent all the time. This can be shown, right? So basically, well, I would like to put a little bit more comments on here. Covariance actually indicates kind of a second order moments. So basically, if your distributions are only determined by first order moment, which means the expectation, and second order, which means mean, and the second order moments, which means the covariance, then it's fine. Correlation is equivalent to independence. But it's also dependent by higher order moments, like third order expectation, like if you need expectation of x cubic to determine a distribution, then it's not necessary. These two things are not equivalent. Okay, now we're gonna talk about probability distributions, which are important for probabilistic learning, right? So, so as we mentioned before, right? So we talk about probabilistic modeling. It's like building a house, building an apartment. You're gonna have some basic units, right? So what are basic units? Different distributions, right? We're gonna use these distributions to construct a kind of a sampling procedure, right? All the probabilistic models are kind of a sampling procedure. Suppose this is your data, right? This is your data, and you make a probabilistic model is equivalent to, okay, I come out a probabilistic sampling procedure from some prior sample some intermediate random variables, and given that intermediate random variables, I sample another intermediate random variables, I continue this until finally I sample the observations. So the definition of sampling procedure determines your probabilistic models. Then once you have worked out such a model, and then the goal is that given the observation, how do you infer those latent random variables in your sampling procedure? That's the whole logic of conducting probabilistic learning. Right? So, but how do we? For example, if I want to measure, like, I have a temperature read, right? I have some read. I can take a look at the temperature read every day, for example. Like today is 74, tomorrow 81, whatever, right? And then how to model this data from probabilistic perspective? I'm gonna work out some sampling procedure that generates those observed data. For example, I'm assuming, okay, there is some like ground truth temperature, which are generated by some state space models. Remember, because today, tomorrow, the day after tomorrow, they're kind of dependent on each other, right? I cannot assume the ground truth temperature are independent to each other. They must be related to each other, right? So I can assume, well, okay, there's some kind of state space prior, which is essentially a Markov chain that generate those ground truth temperature value. And given this value, I sample the observation. Why I should assume that? Because your measurement is always noisy, right? Always filled with errors. I cannot assume that, okay, your device can give you exact rate, right? There are always some kind of corruption, some kind of mistakes made, right? So I have some noisy model to generate the observation. And then I can collect the data, right? After I collected the data, my goal is to, based on this data, I kind of infer what are the actual value for those ground truth temperatures. This is called a posterior inference. This is the ideal situation will be, I can calculate the posterior distribution of those actual temperature values given a noisy measurement. And then, doing this is not easy. In most cases, it is intractable. Now we have to develop a variety of computational methods to fulfill that. But anyway, you must have a probabilistic model in your hand, right? Otherwise, how do you do the model inference, right? How do you ask the model how to calculate posterior distribution, right? And then the basic unit to construct such a probabilistic model is those all kinds of probability distributions. Right? So we're going to talk about those commonly used probability distributions. Of course, this is not going to exhaustive because there's so many different distributions, and in statistical literature, people have like a thorough study of their properties. Right? And from a machine learning person, in most of the cases, we're just pick up some nice distribution and use to model our real world applications. Okay, so we're gonna first we're gonna talk about commonly used probability distributions like binomial, multinomial. These are for binary variable and the discrete random variables. And then we're going to talk about beta distribution and the Dirichlet distributions. So you see that if you want to assign prior distribution over the probabilities, like if you roll a die, right, you got 0.5 chance to have a heads up, or another 0.5 chance to have a tails up, right? So this chance, P, if you want to assign some probability over that, what kind of probability is valid, right? So we can use beta distribution. Right? And in more general case, like if your die has like 6 points, right? 1, 2, 3, 4, 6. Actually, a random variable, the output consists of 6 possible discrete values, right? And the the chance for taking each point, it follows some discrete distribution. No, then the question is that how do we assign prior over this discrete distribution? So a commonly used one is called Dirichlet Distribution. And then we're going to talk about Gaussian distribution and student T distribution. Those are mainly used to model continuous observations. Right? And then we're going to talk about gamma distribution and V-short distributions. We're going to talk about how do you model the variance and the covariance matrix for Gaussian distributions. And then we're going to review the concept of maximum likelihood estimation and map estimation, maximum A posterior estimation, which I believe everyone has heard of these two terms before. Right? Okay, so first we want to, let us first give a general framework about MLE and MAP estimation, because this applies to all kinds of distributions. So suppose, given the data x, we have a distribution x. We have a distribution P of x parameterized by theta. Right? So this distribution could be, say, Gaussian distribution. Then the parameter corresponds to mean and variance, right? This could be some binomial distribution, then parameter just corresponds to the chance you have the head up, right? And then suppose we have observed a set of independent and identically distributed random variables from this distribution, and this is our collection of data, right? And observations, right? Then the natural question would be, how do we estimate data from D? And from the MLE principle, we're gonna find the parameter theta that maximizes the likelihood of all the observations. So likelihood here just means the probability density function of the observed values. So because in most cases we just assume, okay, those observations are independent. And so their likelihood is simply the product of the likelihood of each observation. Then to perform maximum likelihood estimation, we're going to just maximize this product. Right? And a commonly used approach is going to take logarithm over this. Why? Because this density is usually very small, right? It's like, suppose you're doing like if you toss a coin, right? You toss 100 times. You know the likelihood for each observation is just between 0 and 1. If you toss 100 times, the total likelihood, because this is a product, right? It kind of like truncate to 0. So I mean, in most cases, to be more numerically stable, we just take a logarithm over the likelihood, and so that your product becomes summation, and the log likelihood is much more reasonable, right? And then you just maximize the log likelihood. This is the MLE principle. And the problem of MLE is that it is totally data-driven. Given its observations, right? I just maximize the likelihood of those observations. But sometimes we also want to incorporate some prior knowledge about the parameters. For example, if you toss a coin, right, and you believe that the chance you're gonna have a head up is 0.6 or surrounding 0.6. You want to incorporate this knowledge into your estimation, right? And then we're gonna seek for the map estimation. If you don't want to incorporate any knowledge, right, you just look at, okay, you toss a coin for 10 times and just look at heads, tails, heads, all those things together, just maximum likelihood. This is called MLE. Right? But now, if you want to incorporate your prior knowledge about this chance, then you consider the prior about the parameter theta, and then multiplying with the likelihood. Then you maximize prior multiplying with the likelihood, this estimation is called map estimation. Okay. And again, we're going to take a logarithm over that because it's easier for the computation. So your map estimation, you're going to maximize the log likelihood plus the log prior of your parameters. The only difference between map and MLE estimation is that in map estimation, you're going to add an additional log prior term. And this is a, in a non-Bayesian view, this guy is often considered as a regularization term. So you don't want your model to overfit data. You want to regularize the parameters. Right? So you usually put some regularizer. Like a very common use regularizer is just the norm, right? Suppose this is your neural network. This is your neural network parameterized by the neural network weights, right? So it's often the case that when you minimize the loss, this is your loss. So you minimize the loss, will easily get your neural network overfit data, right? And how to alleviate that issue, I'm gonna add up a regularizer to the loss. So I jointly minimize this regularized loss. This is non-frequent. This is non-Bayesian people often doing. They call this guy as a regularizer. But from Bayesian point of view, this is actually correspond to the log prior of your neural network weights. Okay. And then this log prior actually a standard Gaussian distribution. So this is equivalent to assigning a standard Gaussian prior distribution over the neural network weights. Then you do the map estimation. Okay, any questions so far?
Just like the regulator that we have in
SVD. I'm not clear about how do you do regularization through SVD. How do you do that? SVM. I wouldn't say that because SVM is kind of motivated by another observation. It's actually motivated from the large margin principle, from the generalization error bound. They have a bunch of theory. I mean, to give you a foundation on that. But from a Bayesian point of view, we just interpret it as a log prior of your weights. Of course, they kind of like coincide, right? It's kind of coincide, but you'll see like surprising coincidence many places. Okay, this regularizer actually corresponds to a particular prior. Any other question? Okay. And here, I want to emphasize that although map estimation looks a good way to incorporate the prior knowledge, from a Bayesian perspective or probabilistic perspective, is not ideal. Why? Because the map estimation essentially is to find a mode or the point at which the posterior probability is maximum. For example, this is why? Because so first we should be aware that the prior multiplying with the likelihood is proportional to the posterior, right? If you divide by this is joint distribution, right? If you divide it by some marginal distribution of the data, which is constant, this is the posterior distribution. So the posterior is proportional to the prior multiplied with the likelihood. And if you're doing map estimation, this is essential to maximize the posterior probability density, right? This is actually quite restricted because we only know at which place or at which point you can make your posterior density maximum, right? But in many cases, we're more interested in the shape of your posterior density. Like in this case, right? Your posterior density can be quite complicated. It has multiple modes, right? If you use map estimation, you might converge here, you give this point, or you might converge here, give this point, right? But if you can give a posterior distribution of those parameters, that would be much more useful. And this is actually the ideal goal for the probabilistic learning people. Okay, so now let us talk about different.
What is the ideal scenario? Is it just maximizing the mode?
Yes.
What is like the ideal?
Ideal is that, okay, you're not only giving me my point, one point, which maximizes the posterior density. You give me the whole posterior density. You give me the whole posterior distribution, right?
So you want to determine the posterior distribution that
yes.
So that it can after that you can the base of the
yes. You can use base of more optimal predictors to make decisions, or you can integrate into some downstream applications to have a better confidence estimate. Or you can just look at the patterns, right? And this is actually quite important, like in social network system or recommendation system. You want to know, okay, given those data, what is the distribution of users' interest, right?
Since that we have that's a given D up to knowing the probability of data. So the difficulty is in computing the probability of data.
Yes.
All right.
Yes.
And why? And why is it difficult to compute?
Imagine how do you compute P of D? You have to do the integral, right? You have to integrate with your prior and of your likelihood, right? And this integral is I mean, most of practical cases won't be able to compute. It's very hard to compute. It's actually the central challenge in Bayesian learning is to compute this guy, compute this normalizer or data distribution, whatever. So I mean, so people come out kind of a variety of tricks to, you know, evade this or approximate this, a lot of tricks. Any other question? Okay. So now let us talk about different probability distribution, right? So they are used everywhere. I'm gonna stress on this point as well. Again, all kinds of statistical applications, no matter Bayesian or non-Bayesian, they are building blocks to construct more complex probabilistic models. So like 1 + 1 = 2, we should be very familiar with that. So first, we're gonna look at the commonly used probability distributions for binary variables. So consider a binary random variable. That means this random variable x takes either 0 or 1. Right? Like you toss a coin, the outcome is either heads up or tail up, right? You buy something or not buy something, the decision is binary, right? The stock market price is increasing or decreasing is binary, right? It's very common in practice. So we often use the so-called Bernoulli distribution to model binary random variable, right? So Bernoulli distribution is simple, right? We just assume there's a parameter mu, which determines the chance that the random variable takes 1, right? Then we can write down the probability of your random variable in this way: mu to the power of x times 1 minus mu to the power of 1 minus x. Right? If x is 1, then this probability is mu. If x is 0, then the probability is 1 minus mu. Right? And we have nice form of expectation and variance. The expectation of x is simply mu, and the variance of x is mu times 1 minus mu. Okay. And now, suppose we have observed n observations, which are IID, independent, identically distributed, like x1 to xn. Okay. So remember, each observation is binary, either 1 or 0. And then the question is that, how do we obtain the MLE of mu? Or in other words, how do we conduct maximum likelihood estimation to estimate mu, right? So this is just the practice. If you write down the likelihood of your n observations is a product of the likelihood of each observation, right? The likelihood of each observation is this mu to the power of xn times 1 minus mu to the power of 1 minus xn. Right? And of course, for convenience, we're going to take a logarithm, and take a logarithm, you get this summation. Xn logarithm mu plus, we take a logarithm over here, right? It will give this, right? Plus 1 minus xn logarithm 1 minus mu, right? Then you just take the derivative with respect to mu, right? And you solve the derivative being 0, you get your map estimation is simply the average of the observations. So because each observation is either 1 or 0, right? The average of those x1 to xn is essentially is a ratio of the ones appearing in the observation. You take the derivative with respect to mu. Right? You take the derivative with respect to mu. This guy would be xn over mu, right? This guy would be 1 minus xn, 1 minus mu, and take minus, right? I just arrange the terms and set the derivative to be 0 to solve it, right? Yeah. Yeah, I mean, if you feel uncomfortable, just practice. This is kind of good practical example, practice example of MLE, right? So now we can extend the Bernoulli distribution to binomial distribution. That relates to the experiment that you do multiple times of Bernoulli experiments. For example, if you toss a coin for once, the result is either head up or tail up. So this experiment will give you a random binary outcome, and you use Bernoulli distribution. Now, suppose your experiment is to toss a coin for 100 times. And then I'm interested to know what is the total number of heads out of this 100 tossing. Okay? Then this number will follow the so-called binomial distribution. So a binomial distribution is determined by two parameters. First, the mu, which is the same as the Bernoulli distribution. The other is the number of trials, number of experiments, n. Right? So the density or the probability of your x is written as mu to the power of x, 1 minus mu to the power of n minus x. But you need to count how many such kind of cases will appear. Like suppose you toss a coin for 100 times, right? Your observation, you want to know, okay, what's the chance that you will say 10 heads up, right? So you know that for each particular horsing, you might have like the first 10 times you got heads up, and the remaining is tails up. This is one particular realization, right? And maybe you have another case, right? When you do another 100 times try, right? You got like first 10 are tails, but the second 10 times are heads up and the remaining are tails. Right? You still get this probability, but you need to count all possible realizations that include 10 heads up. That's why you have to multiply this combinatorial number, right? N or X, right? Unfortunately, in most cases, this is just constant. You can ignore it. This is kind of a very headache term, but usually we do the map estimation, we'll do MLE estimation. They're just constant. You can throw them out. And for binomial distribution, right? How to compute expectation and variance. So here is the conclusion. Expectation of a binomial distribution, that means independent n trials of Bernoulli experiments, is simply n times mu, and the variance is n times mu plus 1 minus mu. But how do you get that? I think this trick, I think everyone has heard of this trick, right? During your statistical class, right? We don't want to do the expectation, calculate the expectation from the original probability density, right? Why? Because you have to account for this combinatorial number. Right? It depends on X as well. You don't want to integrate X here, right? So common use the trick is that you kind of denote the outcome of each independent Bernoulli trial by some random variable. Right? Suppose you're doing n trials, right? So each outcome you can denote it by x1, x2 to xn. Okay. And then the number of the ones, the total number of ones, essentially is a summation of n outcomes. Right? Then if you want to compute the expectation of this, you just calculate expectation of each individual Bernoulli experiment outcome and add them together. That's where you immediately get this. And then similarly, if you want to do the variance, because you're doing variance of summation of a set of independent random variables, essentially the summation of the variance of each individual random variable. Any questions so far? I believe everyone has heard of this trick before, right? Okay. So now let us extend from binary random variable to more general discrete random variables, which we call categorical variables. Right? So suppose your random variable can take multiple values, right? But it's not continuous. So suppose your random variable can take k values, and k is usually less than 2. We call this random variable as a categorical variable or discrete variable. So we use a k-dimensional vector with only one non-zero entry to represent a sample of categorical variable. This is just a notation, very common use. Like, usually we don't use like x is 1, 2, 5, something like that to represent a categorical variable. Instead, we use the form of this to represent. So all elements are 0, except one element is non-zero. So the position where you have non-zero indicates the value of the category random variable. So this simply means, okay, x takes the categorical 2, right? If you got 0, 0, 1, 0, it just means x takes the value of the third category. Right? So this is called one-hot encoding. So you see a paper, many papers like in deep learning or something like that, or embedding. This word, the one-hot encoding, appears quite often. It just says, okay, I'm going to represent those categorical variables in this form. Any questions so far? Everyone is comfortable? Okay. So we can extend accordingly the Bernoulli distribution to a categorical distribution. How do we extend? We're going to parameterize that distribution by k parameters, right? Mu now has k values, mu1 to mu big K, right? So, and we need to ensure that this k values in mu vector represent a probability for the discrete random variable, right? So that means each mu k must be no less than 0, and their summation must be 1, right? So like you have 3 possible variable values, right? Equal to 3. That basically means, okay, you have 0.1 chance to take the first category, 0.8 chance to take the second category, and 0.1 chance to take the third category. Okay? And accordingly, we can write down the probability of your categorical variable x given a parameter mu by this product. Okay? This is essentially an extension of Bernoulli random variable. Okay? So the product of each mu k to the power of xk. So you can see that the benefit of use one-hot encoding, right? Something like that, right? So you know that every time only one xk will take 1, right? All the other xk will take 0. So that means the corresponding term will simply be 1, right? And only the xk who is 1 will have the corresponding probability mu k. Right? This is a very convenient representation. So again, we can consider how to conduct MLE for categorical variables. Suppose we have n ID observations, x1 to xn. Remember, now each xn here is one hot encoding. Okay? Mhm.
Could you give an example of Bernoulli, which is
Oh, I said Bernoulli extend to categorical. Binomial will extend to multinomial. So like Bernoulli, if you do Bernoulli independently for n times, then the number of ones will follow a binomial distribution. If like, okay, Bernoulli is different from binomial, like categorical is different from multinomial. Right? For Bernoulli, one outcome will be either be 1 or 0, right? But if you do binomial, if you do Bernoulli like 10 times, then the number of outcome as 1 is not 0, 1, right? It can be 1, 2, 3, 4, 5, 1 to 10. Right? So if you're interested in that number, it follows the binomial distribution. It's parameterized by both the mu and the number of trials. And similarly, now we talk about categorical distribution. One outcome of categorical distribution is just a one-hot encoding, right? Either categorical 1, 2, 3, 4, 5. Right? But if you want to do this categorical distribution multiple times, we got a bunch of one-hot encodings. Now, if you're interested in how many times each category appears, then it follows multinomial. Okay, so let us, do this step by step, right? So let us consider that we have n ID observations for these categorical variables. So I just want to emphasize that now each observation is one hot encoding, right? It might be, oh, sorry. You can only have one non-zero entries or something like that, right? Each vector will have a form of one-hot encodings, right? So if you want to estimate your parameter mu, remember this is a probability vector, right? Each element determines how likely you take the corresponding category. Right? And then you just multiply their likelihood, right? And each likelihood is the product of the probability mu k to the power of the corresponding element in observation x and k. X and k is a kth element in the vector xn, right? And then if you merge them together, you see that, I mean, you switch n and k, right? And you can merge the power. You see that it is mu k to the power of summation over all the observations, where for each observation, you just take out the kth element, right? This is actually either 1 or 0. So what this tells us that, okay, you're gonna have a form, a product from 1 to k, where each term is mu k to the power of mk. Mk is the summation over the observations at the case elements. Right? This is something like that, right? This just tells us, okay, how many times in total the categorical k is observed. And then you just take the log likelihood, and then you take you take a derivative. And remember, because the summation of these probabilities must be 1, right? You have to add the Lagrange multiplier, and then you solve this log likelihood. You take the derivative of this log likelihood and set to be 0. You end up with maximum likelihood estimation as mk over n. This is essentially the ratio of each category observed in the data. This is very intuitive. Yeah, I'm not going to show how to get this, but I'll highly recommend you guys to do this calculation by yourself. Right? And now, as we just discussed, right, we can extend our categorical distribution to multinomial distribution. What does it mean? It just means, okay, if you do one experiment, if you do the experiment with categorical distribution for once, right? You got one hot encoding. The outcome tells you, okay, which particular category you're gonna observe, right? So now suppose you do it multiple times. You do it like for 100 times. Then we're interested to know how often each particular category appears. Like suppose you're doing gambling. You're doing gambling and you roll a die. You got 6 possible outcomes, right? 6 categories, 1, 2, 3, 4, 5, 6, right? 6 points. And if you do it for 100 times, we would like to know, okay, how often you're gonna have each point, right? For example, it might be 20, 5, 10, 10, 100. Okay, the remaining should be 55, right? If I'm not wrong, right? So because the summation must be 100, right? So if you want to know what's the probability of the counts of those categories after you have performed many experiments, right? We can use the so-called multinomial distribution to compute. How can we do that? It's very similar to the binomial case, where for each particular appearance, for each particular count, well, you know, one realization of this count, their probability is simply the product of the corresponding probability mu k times the number of appearance mk, right? But you have to add up all possible realizations. Like for example, if I want to get this count, right, 25, 50, right? It might be in one experiment that the first 20 trials are categorical 1, and then the following 5 are categorical 2, and the following 10 are categorical 3, and so on, right? But this is just one trial. There are many other possible trials can give you the same outcome. So I have to count all possible outcomes and as up their probabilities. That's why we have to put this combinatorial number here, right? You got N trials, well, we know that M1 categories, M1 times your categorical 1 will appear, M2 times your categorical 2 will appear until MK times your categorical K will appear, right? So to compute the total number of realizations is just this combinatorial number. And of course, in most of cases, you really do not need to worry about this combinatorial number, especially in MLE or map estimation. You can will them as some constant and throw them out, right? But just be careful. There is some number in front of it to get the accurate probability. Okay, so how are the categorical variables applied in machine learning models? This is, I guess this is something we're really interested in. Right? This is actually this is actually important, and it's very common in real-world applications like image classification. So we know that image classification is a kind of classify. This is a cat 1. This is the first type of cat, second type of dog, and third type of car. Like there are many categories. That's why this is very common. You have to know how do we build a model and then use that model to predict the categories. Then the problem is that, okay, we know this categorical distributions or Bernoulli distributions, we know their parameters either mu or mu vector, right? And then how do we link our model to calculate these parameters? Right? So here are a few commonly used modeling framework. For example, if you're doing binary classification and your outcome is either 1 or 0, right? And then we want to know how do we estimate this mu, which determines how likely the outcome is 1 or 0, right? So often used model is called logistic model. Okay? You assume mu it can be calculated in this form, and this alpha can be some data features, and this W can be some model parameters. And then once you have learned those parameters W, and through this logistic function, you can calculate the parameter mu, which determines the Bernoulli distribution, and then you can use that to determine your outcome. For example, if your mu turns out to be 0.8, well, you can predict your outcome is 1. Right? Because it's bigger than 0.5 is more likely to give you a outcome 1, right? If it is very small, like 0.1, and then maybe your prediction is simply 0. And another common used link function is called Gaussian Cdf. Is a cumulative distribution function of a standard Gaussian distribution. So through any model's outcome into this Gaussian Cdf, it also gives you a number between 0 and 1, right? Remember, this is CDF, right? CDF is between 0 and 1, exactly between 0 and 1. So people can also use this to make prediction. After you learn this W, right, you throw this score into this Gaussian CDF, it can give you some probability. Again, if it is 0.8, you may make prediction as 1, otherwise make prediction 0. Right? So these are for the binary variables. So how about the multi-class classification concept? Right? Remember that we can use a categorical distribution to model the outcome of this multi-class classification problems, right? But then how do we parameterize, or how do we model the probabilities which control the chance of each category, right? Another often used model is called a softmax model. You can assuming you kind of learn, suppose you have k categories, you're gonna learn k group parameters. And then for each category, you're gonna compute the score, this WK transpose alpha, right? And you take exponential, then you normalize it, you get a probability vector, which determines the categorical probability. And then you can use that probability to decide which prediction you're gonna make. Right? Suppose you have 3 categories, and after your training procedure, you got, and using the softmax function, you get 0.1, 0.7, 0.2, right? And then you may just predict the category to be the second one, right? Second category. And of course, there are alternatives, right? So one alternative is called ordinal regression. This is meaning for considering ranking information, especially in like information retrieval, right? If you want to rank the selected result, like I know rank 1, rank 2, rank 3, right? Although they can be viewed as discrete variables, but they have some ordering information. And then how do you reflect? How do you make your model reflect such kind of information? This is called ordinal regression. We're going to talk about ordinal regression later. Okay, so we know that for Bernoulli distribution, it is determined by a probability mu, right, from 0 or 1. And this is the probability density. A natural question would be, what if I want to put some probability distribution over mu itself? Mu is right now also observed viewed as a random variable. Then what kind of proper distribution over mu? A commonly used distribution is called beta distribution. So we can say, okay, we're assign a beta distribution over mu, which are controlled by 2 parameters, A and B. So this is a probability density of beta distribution. Okay. So now this is a continuous distribution. Why? Because mu is continuous. Although it is restricted between 0 and 1, but it is continuous. So don't be confused here, right? Your Bernoulli random variable is discrete, it's either 0 or 1. But the beta distribution over the probability that controls the Bernoulli distribution is continuous. It's continuous. It's continuously between 0 and 1. Right? So you can take a look at the form here. So it's mu to the power of a minus 1 times 1 minus mu to the power of b minus 1. So this is a normalizer. So this gamma is a gamma function. This gamma function is very common used in mathematical analysis. Right? So you can view as a continuous version of the factorial. So here is some kind of curve of the beta distribution density, beta probability density. Right? So if you choose different A and B, the curve kind of varies a lot. Yes. Of course, A and B, you can assign prior as well. So basically, in a Bayesian world, you can assign anything a prior and couple them together. And later we'll talk about if you don't want to assume any information in this prior, how do you choose this hyperparameter A and B? For example, A and 1 and B and 1 is kind of good, right? Because it's kind of uninformative. And this is a common property of beta distribution. If you want to compute the expectation of your beta distribution is A over A plus B. And this is variance. This is not, I mean, you are not required to know how to derive this, just to use them as some conclusion. They are also available in Wikipedia. Okay, I think we can stop here today. And on Thursday, we're going to continue with the fundamental distributions.
question?
Sure.
Simple one. Could you please
Mind if I let me first turn off the